So I mean, I don't have like super formal stuff prepared or anything. We can just have like a pseudo discussion session or something, and then. No.
Definition of the. So you have some kind of master space. Do you see the definition again?
Okay. The master space, you want to see the definition? Okay, sure. So, right. So let's recall what the underlying space is, right? You have some abelian category, and you want to count objects in it. And so associated to this abelian category is a moduli space stack. And draw this as a round vertex.
Stable.
You want to count stable objects, some notion of stability, right? But for now, category as a. So if you think somehow coherent sheaves on some space X, associated to this round vertex will be your sheaf. And actually, for the purposes of pairs in this master space, we're going to talk about global sections of the twisted up as some appropriate high twist. Okay. Yeah. So great.
So if I think filter scheme of points.
Mm-hmm.
That would be, so you take your
You take your ideal sheaf and you twist up or. Well, right now this dot just represents the space of all sections.
Right.
Yeah, but soon we'll pick. It's okay. I mean, this is some vector space. In particular, it contains the point 0. Yeah. So here I haven't said anything about stability or anything so far. I'm just saying point in this moduli space will be some vector space, and that vector space I'll call round dot. Yeah, of course, for stability, you don't want to take the 0 section. That's true. Yeah. I'm pairing.
So,
yeah.
A particular example is like a vector, like a line bundle, and all
like point on the space.
Yes.
And you're asking for a curse of some degree that means this point. Curse of some degree was in section.
Wait. Where am I? So you were struck what point on the first actually VOT.
No. The ideal shape is function vanish at this point.
Okay, so maybe I can be more concrete.
Curve on a third that means to some degree. Curve of degree K that means.
So for concreteness, we can replace this X with like C2 or something, right? And whatever. P2, C2. Character.
Oh, okay.
Okay, gotcha. Sure. So we think. Okay, but whatever. P2 is not so far away from C. Right. So in the category of all parent sheaves on C2, there's one component which corresponds to ideal sheaves of points.
Okay.
Right. So in that case, there will be one component M alpha or some particular choice of alpha, which. Oh yeah, sure. Yeah, sure. And which will correspond to ideal sheaves of exactly n points, right? And so, and this E is then Andre's explaining that this is like, you take some curve which has degree k and you ask how does it meet these n points encoded by I. Yeah. And so I have some vector space of that data. Mm-hmm. That's yeah, but we.
What point not to be on a curve, but to meet a curve, or be on a curve?
It's the opposite. You take the point first, and then you go over the curve.
Mhm,
Like suppose you have 2 points, and you look at all kinds of.
Okay.
mhm, mhm. So that's this vector space. Yeah, okay. And then we had a thing, and so if you just want, you don't really need this vector space. This vector space is some auxiliary construction which we use to get rid of extra objects on E. So we form this auxiliary stack of pairs, which is isomorphic to C. And this round dot is still the data of this vector space. And we're going to pick a particular section in here. So form some collection of all these 3 pieces of data, E, S, and your original point in the original moduli space L. So in particular, there is some forgetful map from M pairs to M, which forgets about the vector space, and it also forgets about the section. And that roughly looks like some kind of projective bundle over M. Here, vector bundle. Yes, that's right. Yeah. Yeah. So K will always be big. Mhm. Curly ambient. Yeah, that's like the Hilbert scheme of endpoints on C2. Yeah.
For each point,
Mhm. That's correct. Yeah. The ideal sheaf. Yeah. Of your subscheme. Z is like side C2, you have a whole bunch of points. You tensor this ideal sheaf by O of K for some appropriate notion of O of K. Yeah, that's correct. Right. Okay. And so you can form this auxiliary stack. And this, you should think of this auxiliary stack as you've kind of taken the original moduli problem and you've added some kind of framing. So there will be fewer automorphisms. Okay. So for any stability condition tau here, there's some lift stability condition to the stack of pairs. So in particular, like Andre mentioned earlier, the 0 section will never be stable for any choice of tau. And you might have some other unstable things, but the key every object is either stable, so it has no automorphisms whatsoever, or it's unstable. It can't be something in between. It can't be what's called strictly semi-stable. And that's in contrast to what happens down here. On the original stack, if you give me some stability condition, there will be some objects in general that are strictly semi-stable. And simplest example being like you take E1 plus E2. So I mean, this Sept has some object. You can pick E1 and E2 to have the same slope, and so it's clearly an object that will still be semi-stable, but it won't be strictly. It won't itself be stable. Okay.
Adding like the foreground on the line bundle.
I think the dimension that there is depending on what your x in different dimensions of the C. And so that dimension of the vector thing is I think it's within the dimension, it's kind of the brain of the dimension of the space.
Yeah.
Okay, cool. So these already know how to count, right? And then we have take some. Yeah. So maybe let me say it this way. There's a freedom to pick this isomorphism, right? And so this stack will always have some kind of C star stabilizer. Yeah. So
okay.
if you
take
up to this choice of isomorphism, that's right. Yeah. So I suppose from my perspective, I always think about moduli stacks. So I always include all possible automorphism data.
Right. It's a question of whether you include this vector space as fixed or vector.
Not fixed. Yeah. So two maps, one to M, to the moduli stack of vector spaces, which are one-dimensional. Yeah. So this is like it's like 1 point, but mod C star. Yeah. So this space itself also has some C star stabilizer. And if you remove the zero section, which will always be unstable, then for suitable tau down here, the rest will be stable, and you'll really get some projective bundle over M of that particular dimension. That dimension minus 1.
Maybe this is not the best example. Maybe think of it instead of rank 1 kind of result, you want our result, and then your underlying function, right. You ask for protection from vector function from the underlying function.
Yeah, so maybe let me so in the category of coherent sheaves on C2, there's R comma N, right? So it matters first what the rank of your sheaf is, and then it matters the Euler characteristic of your sheaf, right? So, for example, if you take this E itself could just be some unstable sheaf or some unstable bundle. So you have some huge stack, which really is the moduli stack, all coherent sheaves on C2. But a coherent sheaf on C2 has some topological data. It has a rank, it has an Euler characteristic, and so on, right? So inside this moduli stack, oh yeah, we're on C2. Yeah. Sorry, I keep getting there's a C2 here. Yeah, anyways. And so for this, this is the components of things of rank R with Euler characteristic N. So in particular, if you take like 1 comma N, you'll get Hilbert schemas. Okay.
You said it, but it's my friend, but
yeah.
The stability condition just changes whether or not F can be 0.
For most choices of tau here, yes. Yeah. Right. So the stable things will really just be any non-zero section S, and it'll form a projective bundle over stable locus of M. Okay. So then when you try to write down invariants here using the invariants here, which we know, at some point you'll face this problem that invariants here will have some non-trivial dependence on this choice of K, right? But it turns out that the invariants we're going to want to write down here are going to be independent of K, and that's a very strong statement. Okay? So you're going to have to prove something about how these kinds of invariants change as you vary K. And that was the source of this Lie bracket and vertex algebra, or that's one way to state where this Lie bracket and vertex algebra really comes from. And so some kind of geometric arguments, you have to form this master space where you say, I have a pair for which I use the integer K1. I have a kind of pair which I use the integer K2. And I want some kind of geometry which interpolates in between pairs for K1 and pairs for K2. And that kind of interpolation is achieved by adding some extra one-dimensional vector space. So now there's 3 one-dimensional vector spaces floating around. And this third one-dimensional vector space, you take some maps into the first and the second. So I can always form some kind of stack like this, which has the data of 3 one-dimensional vector spaces, 2 sections, S1 and S2, and some maps here, which may be 0 or maybe isomorphisms.
What's strange for me with the fact that we have normally items. I'm more used to the somehow interpolated in the frame. We take kind of rank 2 frame, which is sort of pair. If you don't go to something kind of disjoint
Disjoint.
you go to some bigger space.
Oh, yeah, I mean, that's right. No, you're not, no. So these nodes, K1 and K2, they have the same sheaf. So here, here you have a space H naught E twisted up by K1, and here you have a space H naught for the same sheaf E twisted up by K2. Yeah. So I think that addresses your question. Yeah.
So really suppose so I'm looking at say endpoints on C2 and the EK1, I'm looking at the degree K1 curve.
That's right.
S2 is the endpoints.
Yeah.
So it's like I'm picking a section function, like S1, like function.
Sure. Yeah. That's one way to think about it.
Scale.
Yeah.
Picking S2 is picking another function. Like the vanishing node of that function.
Right.
Trying to interpolate between these 2 curves.
Yeah, phrase it this way. So maybe it's good to not read so much into what the geometric meaning of this is, because in principle, the other exact functor of E. Yeah. Well, here we just use global sections of something twisted up high enough, because if you twist up high enough, your sheaf is globally generated by sections. Right. So then choosing this kind of framing rigidifies your sheaf. And it removes. I just mean that, like, maybe here this E has many automorphisms. And choosing this kind of framing kind of removes the.
Visible by.
It'll be visible because it'll change S.
Maybe another way to say it, how does one do this actually abstract? It's going to face it actually abstracted by starting with something like this.
Yeah, that's right.
Take a global section, then go to the module of the algebra, very K, and then the module of the side takes by the sheet. Just look at the has to have this operator. Coordinate function has to X there, you write the equation that this operator can use, and that's the solution to the. So now then of course you have to some kind of teaching basis, and then this is where instability comes in. And so choosing that section kind of spoils the changes.
Exactly. So.
Okay, but maybe with global section.
Oh yeah, sure. Yeah. That's right. I mean, that's why I didn't say anything about exact functors or whatever. I just started writing global sections. Up to natural transformations of the natural transformation. Yeah, that's exactly how you fall into the rabbit hole and never come back in. So let's not do that. So
it is a very question. If I just And now this application.
Yeah, that's for data. I don't know. It's something. I don't have like a super like curve counting interpretation of it. It's kind of like I don't know, it's kind of like you put the whole problem on a P1 or something, and like maybe when this is an isomorphism and that's 0, then you're on one side of the P1. And when this is 0 and that's an isomorphism, you're on some other side of the P1. It's
It could be. There has to be some kind of C-star isomorphism. I don't see what it is. All your
well,
vectors
here.
up to isomorphism.
Yeah. All my vector spaces are up to isomorphism. That's right.
And so isn't this just like saying, I would like one of the isomorphisms to be trivialized?
One of those. I think that involves a choice.
So it's like, isn't this like saying I have like two frames but up to a common?
Yeah, mapping C into mod by C star. Yeah. Yeah.
It's not just we have.
Yeah, so in that sense,
But now you just mod out rank two frames, you mod out by just a scale. And then we have remaining.
something like that. Yeah, that's right.
Huh?
Yeah. Okay. Yeah, all right. Something like that. Yeah, that's right.
Then you were mapping kind of, not. I feel like usually like the map which is something combined like the direct tunnel. You the first one, the first part.
Oh, as in like you want something like this? Like some C2 or something? Map like this? Or something? I think so. I can tell you why this is not so preferable to this. It's because we do want maps from here to the original pair. The original, okay. And here you're going to have some GL2, which acts on this to so at the very least, this part of the diagram has to be what it is. And then the question is just how do you interpolate? Adding one more node.
I mean, kind of, you instead of thinking equation, you be compared with the one to come.
That's correct. Yeah. And the reason for that is we started off by working with certain equations like this, right? And so you want some space that in addition to the data of a pair of equations has something else. So
Yeah.
do I want to think in terms of deep four frames? Okay. Uh-huh. Uh-huh. Yeah, that's right. That's right. Sure. Yeah. No, it's not so much that I want. It's that like you have some diagonal components and you have some other diagonal components. So it's not so natural to hold G.
You would like a product of two projective states, fit in some bigger projective space. Yeah. Or and then more, how would you do it? Or maybe not the product, the union. Some kind of joint.
No, well,
We have to map the ball.
I mean, it's some kind of iterated projective bundle, I think, right? So first you have some projective bundle here, and then over the same point.
expression. Now I'd like to put the union into something and then some more components. So I don't know what it is. No, I still think it's projective space. It's ambiguous projective space where you have projection along one direction, one projective space, projection along one direction.
Yeah, that's correct. Yeah, that's right.
And then the local one.
Or you think of coherence from before.
No, the sheaf stays fixed. So here there's only one sheaf E. It's not that there is a sheaf E1 here and a sheaf E2 here. These two correspond to twists of the same sheaf. So this really maps to M. It doesn't map to M times M.
Here you get some kind of projective bundle over that, and which would you can think of this as, it's really, you have some kind of unstable locus, and then, this is like some kind of simple way to blow it up, more or less. Pick some extra ways.
Sure. Yeah. That's
Pick some extra ways for the projected space. And then now we like two such things about common over the same space. We have some kind of slightly bigger projected space, which maps can go to, and then there's corresponding components will be some kind of focus.
Yeah, I agree with this. Yeah, so maybe what'll help is to think not about what this whole space is, but to actually think about what the fixed loci are under the C star action. Some C
Something, if that's it, what is kind of do it in some kind of thing happen with the building.
yeah, sure.
So is this into some sort of unstable reach?
No, I think it sits over the exact same thing. Yeah, I'll be honest. I don't remember the exact construction of the lift of this thing. It's anyways, so there's some C star which scales this map. Okay. So one fixed locus is this map is 0. Right. Sorry, maybe what is the master space?
Like we need to see, we still need to see how what else if we just this sit over kind of a fixed point in the model. I still don't see how this will lead to any kind of X between two things. X between 2 points and
Yeah. So I'm about to explain that. So we're gonna run C star in this, and the C star action is the scaling of this map. Equally well, you can scale this map if you want, but it doesn't really make a difference. You take if you want to be really invariant, you're taking the maximal torus and PPL torus. So, and there are 3 kinds of fixed locus. One fixed locus is where that map is 0. So, sorry, maybe let me. Let's call this S4. Let's call this S3. Okay. So one fixed locus is 4 is equal to 0. Okay. And what does that locus look like? It looks like you have some. So So this kind of looks like you had the original M pairs for K1. And then on top of this, you have this extra data of what S2 is. That's kind of like a projective bundle over this space, right? And that projective bundle will be like P H naught.
It's just beautiful back on the base, not on the pair. There's two projective bundles in the base.
Sure, yeah, that's right. So right. And then one is, and so if what's the way to put it? Like if you pick the appropriate thing to integrate over the master space, you can cancel out the contribution from pushing along this map. And so the contribution from integrated flow can really be the kind of contribution you want to see from pairs. Okay, so it's kind of like integrate over M master, something of this, of that bundle of like T of this projective bundle over M pairs or something, M pairs K1. Right? So that will cancel whatever localization contribution you get from pushing along this map. And in the end, you'll get this equal to some integral, cup alpha or something like that. And so in the end, you'll get this is equal to the kind of integral you want over M pairs K1. So the contribution you want is the pairs invariant that we care about on K1. You'll have some other fixed locus, which the S3 being equal to 0. And then stability will force S4 to be non-zero. And that's going to be fixed under the C star action because V3 itself has a C star freedom. Okay. The alarm for break time. Okay. And you're going to get the exact same story here. You'll get some kind of projective bundle modeled now on S1. So you'll get something like H naught E in 1 sitting for M pairs in 2. Right? And so again, the contribution from this fixed locus will look something like an integral over M pairs K2. Okay? And that's kind of what we wanted originally. We wanted to relate integrals for pairs K1 to integrals for pairs K2. And it would be great if these were the only two fixed loci. So just imagine, like, abstractly, you want to understand how to integrate things over this. Right? So you have some notion of virtual class here, and you want to understand what is that virtual class and how does it change as you vary from K1 to K2. Right? So what does it mean you want to understand this? It means you want some formula of the sort like M pairs K1 virtual class, and maybe you have some other term M pairs K2 virtual class. Maybe you have some kind of algebra here, right? That's what it means to understand how it varies, right? But how are you going to get such a relation, right? If you want to get something like this geometrically, you're going to have to put this in some larger space, run C star equivariant localization on it, such that the contribution of the fixed loci are this and more stuff. Yeah, that's how you're going to get a relation. Sorry, what's alpha? Yeah. So maybe this is not the best kind of analogy. All that I mean that you have some virtual cycle for M master. It restricts to each of these fixed loci. And when you do that restriction, you get basically the virtual cycle here with some contribution of the normal bundle, right? So if you just cap the original virtual cycle by some term with bundle. Well, yeah, you can handle this one. Yeah. There's some magical integral that you put on the whole master space that cancels out this normal bundle here, also cancels out this normal bundle here. And then you'll have some other fixed locus, which I'm about to explain, where things get complicated.
So it's not like you have a P1 start with precision, wait to this point, you have other fixed points.
Yeah, so what I said earlier, that being a P1 is kind of approximate, right? So here you kind of have something on like the 0 of your P1, and you kind of have something on the infinity of your P1, but of course that's not the true picture because there will be a third fixed locus.
Yeah, but I mean, it's only for like quivers. You have a two-dimensional frame, you scale
right.
One component, and the beginning building for doing fixed locus.
Mm-hmm. Yeah. Yeah, that's right. Okay.
That's the third kind.
Yeah, there's a third kind. That's right. The third kind. The third kind is where both S3 and S4 are non-zero, but your sheaf actually splits. It actually splits into E plus E2, such that up here, you factor through the E1 piece, and here you factor through the E2 piece. And this C star is going to scale. Is it okay? So you have to. Exactly. The sheaf itself has some scaling automorphism. It has some scaling freedom. Right. And so that's. Yes, that's true. But you can undo that C star action using the gauge freedom. That's the point, right? So that was how this is a fixed locus. This is fixed because when S3 is 0, S4 is guaranteed by stability to be non-zero. And so of course, C star will move that non-zero value, but then you can undo that move using the gauge freedom on your vector space V3. Where E is split into E1 plus E2. Yes, only when your E splits, exactly. Right. So you'll have a third fixed locus. So this is like fixed locus A. This is like fixed component B, and then your third component C, which will, well, C will be a whole bunch of components. E can split in many different ways, right? If E has class alpha, you can split as class alpha 1 plus class alpha 2 for any alpha 1, alpha 2, right? So you'll have a whole bunch of components. Let's call them Z alpha 1, alpha 2. Right? And these components no longer sit over the original M. They sit in the locus of M. So the 1 times M alpha at M alpha 1. Some kind of,
really small pattern.
well, it's not like really small, but yeah, it's smaller. Yeah, that's right. Okay. And to answer your original question, Andre, this is where. Oh, okay. Yeah. Right. So right. So what's this locus? It looks like this picture. Except here, you're going to factor through H naught. Here, you're going to factor 1 plus E2 is going to be equal to your original sheaf E. Is it okay? That we really do have this fixed locus? Right. So now imagine what happens when you try to do an integral over the whole master space, right? You're going to get the the entire deformation theory of the master space is like, you have some stuff on top of the deformation theory of M. So you do this restriction of that deformation theory to locus, you're going to have to compensate by what is the normal bundle of this kind of map sum. Right? So here you're going to have some extra term coming from normal bundle of M alpha 1 times M alpha 2 inside M alpha 1 plus alpha 2. And this is the thing that goes about extensions. Yeah. Okay.
There's no statement to the effect that this is the old X in the direct sum.
This is just an X. Yeah.
And then there is some sort of, is there some statement, some integral to zero that master space?
Okay. So you're one step ahead of me. Right. So what's going to, so from this kind of argument that I've sketched, you get some kind of formula like this.
Just for some terms of X stuff that goes in a conversion function.
Mm-hmm.
Also, there's some sort of stuff that
Yeah, there's a little bit more. Yeah. Yeah, that's right. That's right. Yeah. So all the K dependence sits there. That's correct. Yeah. Yeah, that's right. Yeah. So roughly speaking, I get some formula. You're going to which looks like the virtual class for your choice K1, K2, and alpha. Right. This is some known object. Some stuff being appropriately chosen. Cancel out kinds of those on the projective one. It's going to be equal to something like M pairs K1 for alpha virtual class. And you're going to have one extra term from localization coming from a kind of equation S4 is equal to 0. Right? So you'll get like one on this S4 is being scaled by that C star, which I erased, but that star has a have another term. And sorry, I'm not being consistent with where I put my K's. Let's put the K's down here. So this is K1 alpha. And here you're going to get pairs K2 alpha virtual class. And again, you'll have some bundle corresponding to that equation. S3 is equal to 0. So S3 is being scaled by weight Z inverse. And again, you'll have some other line bundle in front. And then you'll get some sum over alpha 1 plus alpha 2 is equal to alpha of some kind of expression which involves the virtual class M pairs K1. Yeah, that's right. Yeah, yeah, that's right. Well, it's I mean, it's O of whatever that divisor is. Alpha 1 virtual, and of course it will involve the equivariant weight Z. Pairs for K2 and alpha 2 virtual class. Right. And hiding inside this function will be something to do with the Euler class of this normal bundle, which knows about extensions. And then there's going to be like a few other things that have to do with exactly what Andre said earlier, that there's some mild discrepancy between what got canceled here, what got canceled here, and what got canceled here by this stuff. Okay, but that stuff is very explicit and it's not as interesting. So
yeah, but this is
maybe
very parallel with I want to like kind of rank two theories to do. I'd like to integrate some stuff, integration of the framing, and I'm gonna get roughly like all partitions on one side.
Yeah, that's right. All partitions go on the side, and then you'll get like stuff in between. Exactly. Yeah.
Kind of X stuff.
Exactly. Yeah, that's absolutely correct. Right. And so the way you actually extract from this is you say, okay, then you take quality and you observe. It's well defined without C star localization. Right? It's like some class that's respect to the C star Z action. Maybe you had to use some extra localization on the level of M, but with respect to Z, this had no. This is like how it works for like almost every kind of wall crossing argument under the sun. I mean, if you read like old, well, not old, but like slightly older things by like Kalkman, or even if you go all the way back to like this master space business of Thaddeus.
Oh yes, master space business is like the whole.
Yeah, the master space thing is really old, and of extracting wall crossing relations using a master space. I mean, this really is not new. It's you really just write down some relation like this, then you take residues, and you say when you take Z, right? And here, well, sorry, I mixed up cohomological. This it's like C1 of L. I mean, I wrote it for class.
This is some theory, just compose themselves to what you said. That's the one.
Exactly. Yeah.
Just compose themselves, you know,
Exactly.
try it anyway,
Exactly. Yeah.
any
Exactly.
shape that has any kind of.
Exactly.
Okay.
Yeah. So somehow this part of the argument is insensitive to even what cohomology theory you pick. Like as long as you have some notion of how to push forward and you have some kind of Euler class and you have some notion of residue. That's the most important. Then you're good to go. Yeah. The actual challenge in this whole project for me was not to work out the formulas, but rather to work out the home for the objects in the formulas. That's the hard part.
Does work in the sense that some things are supposed to live, then C star action, but that's C star action. You find that's what it's but the interpretation there is that you have two intersecting foregrounds and actually live in different worlds. So you have two.
Right. Here you have one instanton.
Right. So then are these the two brains that you have with the H zeros or with no different.
Every time you say the word D brain, I'm just going to stare blankly at you.
That's for them. This is really old stuff. When people have that, have two genetic motions, we would like to put them in some common goal. Something like this. And that's really good.
Yeah, exactly. Yeah. Possibly even from like the same office or like a neighboring office or something. Yeah, that's right. He mumbled something about this being like some widespread idea, but it's unclear how wide that spread.
No, but that kind of modulation is much more advanced. That'd be super cool to have something like this for threefold. Like for threefold, we don't have. I don't know how to do it for threefold. But I don't know. That'd be super.
Even doing it mathematically for surfaces is it's kind of challenging. Yeah. I mean, let's not go to threefolds yet before we do surface. Yeah. Yeah, that's right.
So you're saying that's maybe overkill problem.
Right, that's totally overkill. You don't need to do anything of that sort.
For me, it's not because cross instanton brains, I know brains are. I know what this is brain.
Well,
I'm seeing cook up some sort of example, like Grasmanian flow. This is like a big example, kind of Grasmanian flow. That it means you have some sort of Grasmanian bundle, which is the building is kind of flow. And then you put that stuff into some, that thing. Just or even like whatever Bukai flow, some just like the most basic flow in the world. You can put like you cannot, like if I have a like a long thread, how short change if I flow. And the way to do it is to that sort of stuff. Some bigger space, you localize on that bigger space, and you get you can pick any geometry you want, and you can just right there. But I think it's here's like this is just a choice that will do the geometry.
Is a what?
Because you're saying here, you can just pick up a space, which can be a certain way.
No, I'm just saying there.
There is some space that will do the job for you, and that,
It's kind of amazing general.
yeah, that's right.
Any kind of a sort of basic data to build the problem.
That's right.
You can do that.
Yeah.
For instance, like a class computation, the change of or make people to work out.
Depends on what you're about to say.
Yeah, I know. How they churn classes, how variable to make them.
Yeah, right. I think the Kaufman does.
So string theory construction, I don't think it was much in the beginning, but it was basically.
No,
I mean, this kind of very classical construction does what we need it to do. Yeah. But you know, I'm sure there's many other more complicated spaces that also do what we need it to do, right? But
actually somehow there's still a question, right? Of the like what Henry is about to do is to construct a kind of vertical to the forest, and then but on the purely algebraic, one can see that even though the spaces are different and ones are much more like than the others, but purely algebraic, one can think
right.
whether like Vasily's story. Vasily has some kind of vertex algebra story to show in construction. They don't think of it. One can think whether this is somehow different from the cohomology in terms of just that sort of relation.
Right. Yeah, because the structure of the argument is very, very simple. Like if I was a sleep student talking,
Yeah, maybe the point that Andre and I are trying to emphasize is that this kind of argument structurally shows up in 10 million different places. Yeah, all having to do with either some kind of wall crossing or some kind of flop or. Okay. What were we doing?
So we took the rest.
Right, but if you want me to keep the K theory here, I mean these. Okay, I guess now when we see square brackets with a virtual, this means like virtual structures. Virtual class and some cohomology theory. That's and then you're going to pass some notion of residue, which cohomologically really is residue at z is equal to 0. In K theory, it's some kind of slightly more general residue where not only do you take into account the residue at 1, you also take into account the residue at like every other place, which includes roots of unity, but also includes possible equivariants, like at z is equal to t, where t is some equivariant parameter.
That's in the level of some kind of cylinder.
Exactly. That's right. That's right. So one way to state this residue map that I just said is the residue, which is like cylinder, and you track the residue. That's an equivalent way of saying it. Yeah. And that's actually we don't have to add everything up. Anyways, the way I've written it here, it's kind of clear what the residue here and here is. And then you can prove some abstract theorem that says whenever you've checked that this forms a vertex algebra, either additive or multiplicative or.
Well, actually,
yeah.
Now that for that, now probably some sort of synchronization with virtual structure sheet would really help, right?
Great. Yeah. So exactly. Yeah. So maybe let me write down the equation that starts from 0 first, and then we can talk about the symmetrization of the residue. Yeah. So I mean, when you pass the residues, there's no poles on the left-hand side. You get 0. Here you're going to get like the virtual class. You're going to get the same thing, but for a K2 alpha, and then here you're going to get some kind of bracket. And so using this kind of relation, you can then prove that these the virtual classes you originally wanted to construct are actually independent of K, but not so enlightening. It's just some algebraic computation. So for me, the wall crossing story ends here. And what's more interesting for me at this point is to think for deep. So now let's return to that. right? So I mean, maybe let me write down the formula for what this vertex operation looks like inside K theory, and then we can all look at it. Think a little bit. So I claim that y inside my K-theoretic setup kind of looks like this. You take an input, which is some function which eats a sheaf on the ambient stack and spits out some number. So you eat two of these functions, you'll spit out another function. So if this C lives inside K-homology of M alpha, and this lives inside K-homology of beta, and the whole thing, the output is going to live inside K-homology of M alpha plus beta. And the way it goes is when you plug in a sheaf E, what's going to happen is you're going to take this E, pull back along some map from alpha plus beta to alpha plus beta. You're going to take some kind of degree in the first factor, in the alpha factor, and then you're going to multiply by the Euler class of exactly that normal bundle, which I just erased. This is like the Euler class of the normal bundle of M alpha cross M beta over M alpha plus beta. Right? Maybe with a dual. I don't know. And then you're going to hit this whole thing with the kernel tensor. So now, as Andre observed, if you want to take this formula and you want to pass the residues in Z, in the sense of you take residue as Z is equal to 0 minus residue as Z is equal to infinity, it's kind of important what this ought to look like as a function of Z. And so I think I mentioned this on Monday, but it's definitely worth repeating. If you have functions like, like what happens inside some self-dual theory is theta of Z will be some product, and the product might look like 1 minus some weight tw, 1 minus some weight w inverse or something like that. And that's not so good when you want to take, let's say this is Z. And that's not so good when you want to take residues in Z. And what Andre is saying is that here's the standard you do, especially inside equivariant K theory, where you make expressions like this more symmetric by passing a hat genus. After symmetrization, you'll get something like Z 1/2 minus Z minus 1/2, something like TZ 1/2 minus TZ minus 1/2. And now it's very easy to take residues because you know what the residue as Z is equal to 0 is. It's just equal to the limit as Z is equal to 0. And Z is equal to infinity is it's the same story. So after you pass the residue, this is just going to be something like T 1/2 minus T minus 1/2. And you get very good control over this. So if you want to compute the Lie bracket, symmetrization is kind of important. Of course, then you run into the problem of there's also some Z dependence here, which may ruin your.
That is not exactly right.
What's not exactly right?
Like you have to be T to some power minus T to some other power. Because it's the rest is not more.
Yeah. So yeah, that's right. For n equals a number of things here. Yeah. And actually, this is not so far away from the quantum integer, like.
There's some kind of quantum. There's some kind of index for which you can do kind of quantum number.
Exactly. Yeah. Exactly. That's correct. So when you do things like refined Vafa-Witten theory in the style of Richard Thomas, you'll see these quantum integers pop up every now and then, especially inside formulas for like what semi-stable invariants in that theory ought to be, and quantum integers really come from here. That's like the geometric origin. Yeah. Okay. So there's some this Z here. There's an extra operator which has to record the Z equivariance in the first factor of your input. Kind of comes from the fact that inside the fixed locus of the complicated type, you have some Z action on E1, right? So there's a locus where E splits as E1 plus E2. On the E1, there's some C star Z action of weight 1. And so you have to record that somehow when you run this localization calculation. And so it could be that your self-duality is being upset by it. So actually, this calculation only goes through when you plug in things like the structure sheaf, where you're guaranteed constants. And here you always have some Z that comes from the normal bundle, and so then you
But somehow it's okay to somehow not just the rank.
it's okay. It's not as nice. Yeah, that's right. I mean, of course, you'll get some formula for the Lie bracket. It just won't be super nice.
No, but it's just saying what it says. It says that in my kind of I have some kind of X bundle. This records date with the rank. Then the tree switch.
Yeah, there's some like higher tautological classes. That's right. Yeah. Which is what you would expect from some kind of. Yeah. I completely agree. One can do that calculation. It's just the formula is not, is what you write something like, Z of alpha, Z of beta applied to O equal to the quantum integer chi alpha beta T of Z alpha plus beta of O, right? It's like as clean of a relation as you can hope for. And so more generally, if you plug in something that's not O, I think over here you'll get something like some various Chern classes or Chern characters of the thing you plugged in, plus various Chern classes or Chern characters of this normal one. So some formula like that exists. Okay. So I should say, like, somehow the fact that this expression that I wrote down here forms for you a vertex algebra. This is completely formal. You just have to assume something about like some kind of some compatibility of this object with this pullback, and some compatibility of this object with this Z to the power of the degree operator. Once you assume these kinds of, the proof is just really formal. You can check like whatever set of vertex algebra axioms you use. So like you can check locality, you can check blah, 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 blah. So the main challenge actually was to find some kind of mathematical home for expressions of this.
There's no locality here.
I mean, there's no locality here because here everything's in terms of rational functions.
In the locality, you really have no singularities other than the diagonal.
That's correct.
Which is not the case here. That's like your opinion for
oh, yeah, that's right. I mean, maybe we shouldn't call it locality or something. Yeah, it's like some kind of equivariant locality or something. I don't know. Yeah. I mean, maybe the right name for it is the more mathematical name. I think usually it's called something like weak commutativity or something like that. So all that is really, really formal. So the main what's the way to put it? The main like actual issue with constructing these kinds of vertex algebras is you have to work in some kind of context where, for example, this pullback always exists, right? Because this sum map can be horrible. It doesn't have to be flat or proper or basically any kind of adjective you have in algebraic geometry to describe morphisms, probably it's going to fail for the sum map, right? So in my setup, it's kind of important that you only ever plug in vector bundles or more generally perfect complexes. You can't just plug in some arbitrary sheaf. And there are more general places where you can construct this kind of vertex algebra. And you just have to make sure that in all those places, these arbitrary pullbacks really exist. So for example, you don't have to do this in ordinary K-theory. You can do this in critical K-theory as well. And in critical K-theory, as long as your ambient space is like smooth, right, then all pullbacks you ever want to write down exist, because coherent sheaves on some smooth space, they're the same as vector bundles, at least in the K group. And you can always pull back vector bundles. So whenever you can make sense of formulas like this, you always get some kind of vertex algebra. And that's purely formal. That's what I want to emphasize. Okay. Shall we maybe do an example on vector spaces? Is anyone interested in that?
If I just in the old graphic here,
Yeah.
if I just consider, you know, kind of partial superposition, and then I have like this kind of growth term, that was an example. I don't know if
I think it's kind of important that you're on stack, because this map is it's kind of yeah, maybe. So I mean, yeah. Right. So there's three kinds of things you would need on your space in order for this kind of expression to make sense. First, you need some map like this, which you have in the case of instantons. But you also need that every object at least has to have some notion of automorphism. So no, this degree is kind of like on the stack M. Assume worth of scale morphisms, right? And K of M Z graded. So the assumption map, like point mod C star, is going to M.
Okay. And then
No, I'm not objecting to thinking about instantons or things like that.
There you have like a kind of K-theory class.
No, I don't think so.
If I have a torsion sequence the structure sequence is T.
Yeah.
Then okay, it has a right?
Sorry, maybe I can give you an example. I mean, here we can take M to be the moduli stack of vector spaces. So it'll have a thing, have a certain component, point mod GLD, right? And what does the K theory of point mod GLD look like? It's like, you know, K of this thing, symmetric polynomials, Laurent polynomials in D variables.
Right, and there's a central GLD.
Yeah, exactly. So you want each of these variables to have degree 1.
Right. So if I think, you know, GLD is being kind of constant of my position.
Yeah, correct. But for the thing to make sense, you have to be working already on the stacky level. You can't just take this moduli space associated with it. Oh, okay. Yeah. Then I think it's fine. Yeah. I don't see any problem with that. Yeah.
There's a great number of authors.
I mean, the grading will just be whatever degree polynomial you have in in your boxes. Yeah, that's right. Yeah, so you will get some vertex algebra there as far as I can tell. But precisely what that vertex algebra is, I can't say, because it's already a hard thing to say what the state space for that vertex algebra is.
One node, one loop.
Yeah, right. So, well,
Give me just
Oh,
the
what?
data. Just scribble one node and one loop.
yeah, let's not even talk about the loop. Let's just do a quiver with one node. Is that okay? Okay. So we go back to linear algebra and think about vector spaces. Okay, so right off the bat, we need to compute what mod GLD. And any good notion of forget it. Okay. And I don't want to.
But that's your grade.
Yeah, but we're not. So for me, the equivariance is some extra equivariance on top of that.
Right. This is the business. Okay,
Let's just compute non-equivariant. So let me do what this is.
you shouldn't use the word define. I don't think anybody can
Okay, let me write down the definition of what this is. Okay. So have an element in here. What does it mean? That's the collection of maps. The collection of maps phi sub s, okay, for any stat s. And these maps are maps from ordinary K theory, or maybe K per. I'm going to start distinguishing between K of sheaves and K of vector bundles, just because everything here is a point, and points are smooth. Okay, so we map the K theory. Trivial fibration over some base S. And it's going to map into K of the base. And you should think of these functions as some kind of integration along fibers. That's what these will end up being in all of the geometric constructions of interest. Okay. And all of these phi s's, phi sub s's, they have to be natural with respect to, if I have some base S and you have some other base S prime, and my base maps into yours or something, then pullback along that map should be compatible with these phi s's. In the cases of like, like vector space mod group or something like that, K theoretically, there's a Kunith term that says K is, like point mod GLD cross point mod GLE is of course the same as K GLD tensor K. But in general, this is not true. Even if you work non-equivariantly, this is not always true. In fact, it's mostly not true. And if you do want to work, there could be a what? I'm just making the very general statement that you do not have Kunith theorem in general of the yeah, but here it's fine. Here it's fine. Of the form point mod a group, or more generally, always some Kunith property, like point mod a group times 1 will always just be this. And this you can check. Okay. And for this reason, we don't actually need to work with the collection of all these maps for arbitrary S, because everything's going to factor. And the only piece of data in here is phi, which will be a map from K of point mod GLD into K of a point. Okay. So in this kind of setting, we only ever have to think about maps like this. And then on top of this neutrality condition, we're going to impose what's called the finiteness axiom. Okay. And that's what will make things really hard. What does finiteness say? It says that inside the group, so the augmentation ideal, it consists of all rank 0 things. So in this case, you have some Laurent polynomial ring. Yeah, it's the ideal of those vanishing at 1. So like you have things like 1 minus S1, 1 minus Si. Okay. And what we're going to impose is that if you ask, what is this when you plug in things in high anticipation, answer is you want this to vanish for sufficiently high powers. Okay. So this is some condition that you. That's correct. Yeah, that's correct. So when you have no equivariance, this is kind of okay. So when you have no equivariance, it's exactly what you. But then Kuhn theorem, right? Then these phi non-trivial S actually contain more data, and then it's kind of hard to formulate what should be here. It's something about like if you take the map into a higher power, the augmentation here. I don't know what to make of that. But when you have a Kuhn, that's correct.
So now you say when you look at the algebra,
Sorry. It's the universal melting. It's like the yeah, that's right.
Okay. You took identity of the group. Distribution support that
that sounds roughly correct to me, but I can give a more geometric description if you want. It's, the punchline is that the group of these functions satisfying this finite condition is really what the topologists call the topological K-homology group of the topological realization of this. So I'll show you why. So what we need to ask for functions vanishing on sufficiently high power idea. It's kind of like asking for continuous homomorphisms from something like K of point mod G into K of a point Z, where this has the iadic topology. Maybe let me say it this way. If you're going to vanish on high enough powers of the augmentation ideal, it doesn't really matter whether you think about maps from here into Z or from the iadic completion of here into Z. So let's see, continuous equally well. This is going to be equal to hom continuous. Is that? And there's a theorem by Atiyah and Siegel that says exactly what this is. This is the topological K theory of BG. So for example, if G is C star, you're really going to take like the usual topological K group of CP infinity, and you're going to think about functionals on it, which are continuous with respect to that topology, right? So the G if G is C star, right? Then what's
Is that polynomial one there?
you're going to get polynomials in one
It
variable.
is essential to universal.
I didn't disagree with that claim. Yeah. So what's K of point mod C star? This is like Z Laurent polynomials in one variable S. What's I is the ideal 1 minus S. The completion is K of CP infinity, is going to be Z power series in 1 minus S. Right? And the continuous functionals on here, these are spanned by some dual basis to these monomials, 1 minus S to some power. So what are you thinking? You're going to get that K-homology of is going to be something like Z polynomials in one variable phi as usual. This is as Z module. And what does phi do? Phi to the K, which is some element in here. If you plug in some actual like sheaf on point mod C star, plug in S to the n. This has to spit out for you some integer. And what integer does it spit out? It spits out for you the binomial coefficient n choose K up to some sign. So you get points. And of course, it's not so hard to believe that you then replace the C star with a group G. You ask, what's the operational K homology of point mod G, or just GLD? You're going to get something like Z phi1, pn, symmetric polynomials like this, something like this. D. So in this case, we can actually explicitly compute what this state space is. But somehow, like, you can imagine more general situations where you have some equivariants that you care about, and then you don't have some Kuhn theorem, or you have some equivariants that you care about. And there is an extra axiom which I've left out here, which says that these functionals have to be compatible with some kind of equivariant. Then it's not so clear what happens in these. And in the case you don't have, that becomes even worse, because what you mean by equivariant localization could change space S. So somehow the problem is that I've written down some like gigantic group called equivariant operational K-homology that has the bare minimum necessary to run all the arguments I want to run. But somehow that group is way too big. It's very unclear, like, the entirety of what it encompasses. It certainly encompasses what we need, but it has so much more stuff. And so maybe part of the challenge is to say, like, is there some way to impose like maybe some slightly stronger axioms or like something else to shrink the size of this group down into something more manageable and something more understandable? I don't know how to do that. Okay. But at least for the quiver with one node, this is our state space. Okay, summed over all D. And then we have that formula from before. Okay.
Some kind of distribution order. Somehow some distribution on the order.
Okay.
Would that not be somehow automatically compatible with the relationship because you're ordering KP is compatible with the distribution?
Well, so you have this problem that what you're saying is true when you're working on K-theory of schemes. And that's because the fixed locus of a scheme always injects into the scheme itself. And what happens for stack, the correct notion of the T fixed locus of some non-trivial stack is the data of some T fixed points and also the data of elements in the stabilizer which commute with T or something like that. Right? And so the T fixed locus will be strictly bigger than the original, what you would call the T fixed locus in the course module. So there's some stacky complications that happen. Which is why, like, I don't write down some axiom that says if you think about some map, K per T from our stack into K per T point, the axiom is not that this has to factor through K per T of X fixed locus, whatever this means, right? This is some super complicated object. The actual axiom is that it factors through some stack. I don't care what it is, as long as the T action on here is trivial. So this is totally fine when actually this phi is some function supported on some scheme theoretic locus inside X. Then it's fine. Then you take this to actually be the T fixed locus in that scheme. And that's okay. Then what you're saying is completely true. But because we have to think about functions on the entire stack, something like this becomes more complicated. I looked for a while if there's some note of the stack that really doesn't introduce these additional complications, but it really seems like there's only one good notion of what T fixed locus for a stack looks like, and in general, other than X, some like larger object. You can ask that. The structure. So that's fine. Saying that it factors through. I don't care if it's actually the whole thing. So for example, when this is supported on the scheme theoretic locus, this really can just be the fixed. That's somehow the moral of the story is that everything is more complicated when you have to work with the stack. Right. So then once you've identified this space, you write down the exact same formula, which I erased. It's going to be answer C applied to, and here we can really say this theta. So what is theta? Theta is equal to of what? Of the normal GLD cross GLE into G. It's clear what this normal bundle is right? Like the tangent bundle will be HOM of universal bundle, universal bundle, and here it's going to split. So you're going to do something like, let me just write it down. It's some product I less than or equal to D, J less than or equal to E. So here I'm assuming this phi is somewhat. What do you mean?
Since you have a variable,
I'm gonna have some variables.
that you apply the differential operator, more or less. What is the operator? What's the dynamic operator? Why? Differential operator.
Oh, here. Yeah. Like some kind of d by d, like 1 minus s or something.
Right.
Yeah.
Well, no, it's just really the f by the
It's, yes, that's correct. Yeah. Right. Sure. Yeah, that's correct. But annoying thing is that you have to pick some which is well behaved. You have to pull back along some, or the thing that you plug in. Right, so here, plug in some e, and so here the kernel of this transformation is something like 1 minus z si over sj, 1 minus z inverse sj over si. And what's this back along some? It says you take some symmetric polynomial in d plus e variables, and you treat it as a symmetric variable in your first d variables and a symmetric polynomial in your last e variables.
I actually see why you have the same variable.
Same variables. I could be more. So, that's right. Say point mod GL. This is S, comma I. Here I ranges from 1 to D. So then here you're going to have S D. You're going to have S E J S D.
You have a chance to know variable X and Y, you don't know the L, D, I.
Sometimes you. Okay, you can call these variables whatever you want. Anyways, so this is the formula for your vertex operation on your state space. I don't know. It's a good question. If you do this in homology, in the additive setting, you get some formula which kind of looks like this. And then you know for ordinary vertex algebras that you have some kind of reconstruction theorem, which says that if you know your vertex operators and how they act on certain modes, then you can reconstruct your whole vertex algebra. So then if you want to check, okay, is my vertex algebra equal to something known? All you have to check is this formula producing for you the right thing with certain inputs? And there you can show that if instead of working with all work with homology groups of whatever the entire derived stack is, what that means is that, like, imagine what happens when you vary d, right? First you get GL1, which is some polynomial in one variable, and then you get GL2, it's two variables, and so on. If you pass to the entire derived stack, apparently what happens is that for each component, you just get the ring of symmetric functions. So you have countably many variables in each component. So even for point mod GL1, you're going to have literally the ring of symmetric functions. And that is at least like something you have to have for some lattice vertex algebra. So the result in homology is that via the reconstruction theorem, you can just check that you get a lattice vertex algebra. Here with the lattice being the stupid lattice, like a one-dimensional lattice. But inside K-theory, I don't know. Maybe you get this. First of all, I haven't proven that many things about like abstract multiplicative vertex algebras, but I imagine there's some kind of reconstruction theorem that you can prove.
First of all, there's not this kind of effect we have in this situation. We don't have any kind of effect that we have both in away from that.
Or you have what?
You don't have any kind of effect here with full.
Yeah. Here, so here I've written things non-equivariant, and you don't have any of this multiple cover behavior. So really, you have something that should be completely the same as the usual lattice vertex algebra, except written in some multiplicative language. That's what I would expect. Yeah, it's true. Yeah, but if instead you start from some more complicated quiver, that's not just a point, right? Then on the edges of that non-trivial C star action.
Yeah, but that's what I was trying to say from the beginning. When you have, two things which now represent kind of young data, you get top of your value, you have like table, and then you have more.
That's right. That's right. And so then you'll get some kind of denominator, and your denominator will have things like Z, maybe some weight T, and some stuff. And then there it's really not clear to me what this vertex algebra is. So I'm making the statement that without all this nonsense, so with no equivariance in the case of a point, you get something which should be just some multiplicative version of a lattice vertex. But with the equivariance, like if you have some non-trivial quiver, then I really don't know what you get. I don't know. You can already ask this question for this whole setup inside equivariant cohomology. You don't have to go to multiplicative vertex algebras. I think it would be a great exercise to work this out inside equivariant cohomology. See like some equivariants like usual vertex algebra, and presumably that's some kind of equivariant refinement of a lattice vertex algebra.
I maintain what I was saying yesterday.
You what?
I maintain what I was saying yesterday. Equivariant derived category. All of your, which is much bigger. Stuff where you take every object but then in the end in there your forms are really invariant. So those are kind of building blocks. This is composed other equivariant stuff is composed.
Yeah, that's to be explored. Yeah, so that's the simplest example. And so you see, it's kind of it's kind of pretty far removed from like coherent sheaves on an AN surface. I have no idea how.
But there is something very similar. Right? You have some.
I mean, there the formula will be similar, of course. The formula is always the same, right?
It's just that.
That's the question. The question is, what's the space? Formula is always the same.
It's going to be some sort of it's a quotient of vector space by J, right? If your space is going to be slightly, and someone slightly decorated, the polar space.
So for coherent sheaves on some certain Nakajima quiver variety, yeah, okay, yeah. Maybe without equivariance, I'm willing to believe that. With equivariance,
With the equivariance, it's just you have with the equivariance, you have some stuff like all possible equivariant shapes and stuff of this, like some kind of basic and all the equivariant shapes.
No, I'm not worried about what the group containing P looks like. That group is fine. That's just the usual equivariant K theory of Nakajima quiver varieties, or maybe the stack, right? But then the question is, what is this K-homology group? Right. It's some group of things.
Instead of evaluating one, you evaluate all possible kind of shifts. You have some kind of distribution support for them, whatever. All possible. Some kind of homology. Yeah,
morally speaking, that's what this should be.
So
yeah, that's right.
Like you have a group equivariant. Look at all possible homomorphisms from your group to version. and you kind of completed all those places, like differential distribution.
Yeah. Right. Yeah. So that I think is true, assuming a Kuna theorem, so that you don't have to worry about neutrality. Then I think you're okay. Yeah, maybe something like that.
So you don't want to think of the equivariant Graph category as just the ordinary Graph category to keep track of grading. Of course, you can think that all the morphisms are invariant by introducing many more objects, but at the end of the day, I think the natural, I mean, there are two things you can think of. You can either actually force them by the equivariant action, in which case you get, in physics, like if you're really gauging the action, so I got it here in the smallest space, or I just think of my original theory, I just insist it has a symmetry, and I keep track of all the
Right.
and then it's not more complicated. It can't be possibly more complicated. It's actually more rigid.
Right, but you're right. But what I was trying to say is this: suppose you have some theory. Let's imagine this like some kind of logic algebra doesn't have that kind of words. If you have some theory in which you have poles, not just as you have some object of position kind of Z, some object of position W, and you just don't have poles just when Z equals to W, but also have other poles with Z and W shift by different by whatever T1, T2, or T1 times T2 cubed. That is what is involved in physical. You have some kind of system, another system. You have all the kind of extra poles in the interaction. That will say this is a component system. There's some kind of coordinates here, some kind of coordinates there, and I can just I can try to decompose my object according to their kind of core comments, and then for them the interaction is the actual pole, the actual stuff.
Yeah.
And the home for this is I think the natural home for this is when you, instead of working with your kind of the thing we like to, if I have a group action, it's math, it's kind of a group action that acts on the space of morphism, and you can keep track of that action. But there's another notion of the green for this, the equivariant Graph category, in which you require all morphisms be equivariant. That means you get your I think very it's not really different. So that's not
But it's just you need to stick with the fact.
right, but this is not something, it's just different. So if you're looking for, exceptional collection. There'll be something of infinite exceptional collection, which is relatively new to but it's but that's, it's just something slightly different sometimes. You really take an object and really break it into some things which are no longer allowed. I don't know. I'm just saying that there's maybe some simpler underlying vertex algebra in which all the interactions are bad, of which this guy is some sort of this guy sits there and object like if you have precision. So precision. Really we're going to think it was composed of all the boxes and the way they interact and that's like the function we're going to write here without some kind of X stuff, right? The actual characters they're really products of the box. It can make sense to think of this as some collection of boxes. So don't repeat. I'm just saying that in some sort of sense, the precision is all the boxes, which represent like a collection of one box, many of the topics, but also.
Maybe to try to rephrase that, we're saying it's possible that this large operation where you eat something like this, which has poles at like Z is equal to WT for various T, maybe there's some factorization, like with some TI here. These operations only have poles along the diagonal. Like truly the Z is equal to W diagonal or something like that. That like maybe one algebraic way of yeah, but the problem is Yeah, the problem is this part is fine. This part, of course, the doesn't product. Yeah. Well, I mean, here, I don't know. Maybe the thing to start with, in this case only, where functions really have interpretations as some differential operators, and then maybe there you still have some factorization property. In general, it might be hard to think about what these are. I don't think you can always think of them as some kind of differential operator.
You think of this as something to do with the K-theory, all these functions.
Morally speaking, I agree.
Every ring of functions. What about the future functions? They still have total credit?
It's kind of up to you guys.
How much they covered today from what you were?
I didn't really have like a set plan today. I mean,
But you had some plan for like private.
yeah. So I was going to explain. Let's see, what was I going to explain? Right, I was going to explain this work in progress, which is almost finished. That, you know, here you have some vertex algebra on something which looks like homology, and often on the cohomology of the same kinds of space, you have some Hall algebra, and there's a theorem which is mostly proven that these two kinds of structures will be compatible. Right, so, but you have to be a little careful when you formulate that kind of statements, because you're going to have to take what you've written in homology, dualize all the axioms and all the objects in the vertex coalgebra on cohomology, and then you show that that's like a Hall algebra morphism or something like that. So there's some theorem to that effect. And I was going to explain something about what multiplicative vertex coalgebra ought to be, because that's really like not as obvious as one might think at the beginning. And then I was about to explain like that not only can you construct these vertex coalgebras on the K theory of things, you can also construct them in critical K theory, which may be helpful for you know, studying things that are not covered by regular K theory. And the vertex coalgebra is much simpler to study because it essentially strips away this stuff. And so that's some structure that's like super easy to play around with. I was going to explain something along those lines, but that's very much work in progress. So it's up to you guys if you want to hear something about that. Yeah, it's true. But there should be at least one person that's interested. that's the requirement. And of course, I'm very happy to answer any more questions about this stuff too.
Do you have a way to write some known vertex algebra
In this language?
in a form like that?
No, I don't know. I don't know. Maybe what is vertex algebra? It's already hard enough without the hat. Yeah. Well, yeah, I mean, there it's going to be, I mean, via this from the one else, the homological.
Yeah, but it has to be, Oh, I'm not thinking this.
Oh, like you want to write your vertex
this kind of-
operator in this.
kind of shuffle.
I don't.
Can we just tell the story completely here in this one example?
Okay.
What are the variants and what are, you still would sort of add the framing now and then stabilize it.
No, so here, right. So the origin of the vertex algebra is in that kind of story. But to actually work with the vertex algebra, you don't have to think about that at all. To actually work with the vertex algebra, you just know what is this K-homology of these stacks. And here I've done that computation for the stack of representations for the quiver with one node. The answer is you'll have a component for every positive integer. And the component corresponding to the positive integer D is this group.
Going back to the whole story.
Yeah.
I mean, this quiver with one node,
Yeah.
it's supposed to have a single bounds that only for these. Right, if you don't add anything.
That's correct.
Can we keep
Fact that if you want some stable points, your D can't be bigger than 1. When your D is bigger than 1, most things are unstable. Yeah. But the vertex algebra is just some object that lives on the entire stack. It doesn't care.
One,
Okay.
you did that because it's the vertex algebra, so what are they, how do they connect all the things?
Mhm.
And the other one, actually, what are they speaking about variations of stability? How could I, if I were things that I know?
No, the vertex algebra knows nothing about variation of stability. It's just some tool that's used to encode some formulas about variation of stability. It's kind of like asking like you know, what do Andre's quantum groups know about quantum multiplication? I mean, the quantum group itself doesn't know anything. But it's convenient to express these operators of quantum multiplication in terms of the quantum. Yeah.
You think you're gonna get it with yourself?
Yeah, that's correct. Yeah, that's not. I think that's a term.
It's, you have, what's written here? Your element in the vertex algebra is something differential operator.
Mhm.
You apply the differential operator to some function in the value of 1.
Mhm.
That's how you.
Sorry. There's no evaluation at 1. The vertex algebra produces some series inside.
Right, but you evaluate ethically.
Why am I evaluating the S? When you apply your differential operator. Yeah. Right. Okay. Yeah. Ignore me. Yeah.
It's like, and, you know, what, if you have, suppose you have a function, on functions, you have this sort of thing, like. What would be operational function? There is function, you know, function, k variable, function 2 variable, function 3 variable, make 5 variable, you multiply by some weight, with all the x in your quiver, and also if you have more than one vertex, then you'll have
Something to
some
do with
set
the
of variables
edges.
for each vertex, and then the symmetry.
Mhm.
Now the dual operation for that would be, we won't need to symmetrize because we're going to already apply the invariant differential operator.
Mhm.
And operator is already invariant for you to symmetrize, to apply it. The other is one that's like a dual operation on differential operator. So what Terry is saying, that operation is going to be
Forms of vertex algebra.
important for the function. Now, you maybe think about it like any kind of operation on the group. If it uses operation on functions, if you have like if you have multiplication on the group, then you have a co-product in function. And then on differential operators, you have the dual multiplication in the group. It uses convolution differential operator, which is multiplication in universal algebra. So B, you also have an operation, you can put two groups together in a digit. And that involves one function that does something like a shuffle product, an invariant function. And then on invariant differential operator, it uses some operation.
You get this.
And Henry says that it's very generally averted.
That's right.
And that's what it's gonna be for arbitrary quiz as well. I mean, it's some sort of, it's fair to say it's like a duel of the shuffle.
Yeah, I think so. I think that's fair to say for quivers.
So it's like saying, more or less, it's like saying you have a duel of a quantum group. And there you find it.
Yeah, that's correct. Exactly. Yeah. So one application of this theorem that your vertex algebra is going to be compatible with the Hall algebra is that there are certain Hall algebras which literally are supposed to be quantum groups. And so in particular, you'll get some vertex algebra which lives on the dual to that, which literally is compatible with the quantum group itself.
That coproduct is also the big infinite slope coproduct, or is there some sort of?
I don't know.
I should. I apologize. I should, especially since this is recorded. I should put stuff like this, but just like the shuffle algebra, direct. I mean, I shuffle algebra coproduct.
No, I don't know, Andre. Because yeah, so I mean, if you want to approach quantum groups from the perspective of shuffle algebras, the way I know to do that in K theory is you have to form these critical K group critical like K theoretic Hall algebras due to Tudor. Right?
No, I don't. We don't. For quivers, you don't need that.
For quivers, you take the K theory of the pre-projective stack, and that forms for you some pre-projective Hall algebra, which is supposed to be isomorphic to the positive part of your quantum groups. But to actually like get this kind of pullback, you're going to have to pass to critical K theory anyways. So it's best to interpret that kind of shuffle algebra as coming from the critical K theory.
The shuffle algebra should be just really top of the quantum group.
That's correct.
Yeah, I mean, regarding the structure.
Yeah. So
the shuffle algebra has some natural coproduct too.
yeah, that's the thing. I don't really know if there's a good understanding of what that coproduct is. I mean, of course, you can write down something abstractly, which is what Tudor does.
But it isn't roughly communicated. Or is it because that stuff, the shuffle algebra, the shuffle algebra formulas, they're usually roughly commutative.
That's correct.
Means the two things are play more or less the same role.
I understand. Yeah. I don't know.
And there's all possible coproducts in the quantum group, but
right, which is commutative. Yeah, that's right. That's right. I think you should ask Tudor, not me. I don't know that much about this shuffle algebra side of the picture. I know enough to prove it's compatible with this.
You have big.
Well, he's maybe less happy with K theory than some other people. Yeah.
That's the question you know about.
You can also ask in cohomology, but in cohomology, and inside cohomology, I don't know. It's psychologically harder for me to work with critical cohomology than it is to work with critical K theory. It's Z and Z inverse. It has to do with the fact that the normal bundle to like cross Y. That's right. Has to do with the fact that like if you take X of something like V1 plus V2 self-Xed, and you remove the part where you have the self-Xed of V1 and the self-Xed of V2, you get some cross term, and then also it's swapped. Yeah, so.
Yeah, but in fundamental, I think this is a couple of things.
No, because
Z.
In one factor.
Yeah.
So it's going to scale, one fundamental one way and then the other fundamental the other.
So if you swap the two things.
One kind of goes, this by fundamental is going to scale one way and the other by fundamental is going to scale the other.
Shall we call it a
I
day?
propose we have another multiple Friday. Also, I'm curious, anybody wants to do this tonight? It's kind of work hard. Or are you free for?
I'm free for tonight. Yeah.
Yeah, we can discuss about the impression.
It can be you, me, and the computer.
Yeah, right. Are you just coming back to that?
Well, thanks everyone for your attention. This was recording the whole time.